So now we're going to be looking at standard enthalpy changes of reactions. Okay, and we're going to first define what is meant by the standard enthalpy change of a reaction. Okay, the standard enthalpy change of a reaction. The standard enthalpy change of a reaction. Okay, we use the symbol delta H with a theta as a superscript. Okay, to denote the standard enthalpy change. Standard enthalpy change of a reaction is defined as the enthalpy change. Okay, the enthalpy change when molar amounts of reactants as shown in the stoichiometric equation as shown in the stoichiometric equation react to form products. Okay, react to form products. Now this is just the enthalpy change of a reaction. Okay, to form products. Right? If you were asked what is the enthalpy change of a reaction, you would say this is the enthalpy change when molar amounts of reactants as shown in the stoichiometric equation react to form products. When we're talking about standard enthalpy change of a reaction, right? The word standard here simply means under standard conditions. Okay, it means under standard conditions. Okay. So that means that we're determining or we're determining the enthalpy change at 298 Kelvin and 1 atmospheric pressure. Okay, that's what we mean by standard conditions, right? Room temperature and pressure, right? And this symbol theta represents standard conditions. So if I show you this symbol for the enthalpy change of a reaction, it means that enthalpy change was determined at 298 Kelvin and 1 atmospheric pressure. Okay. So again, the word standard simply means under standard conditions. So if you were asked what's the enthalpy change of a reaction, it is the enthalpy change when molar amounts of reactants as shown in the stoichiometric equation react to form products, right? But when we talk about standard enthalpy change, it will be under standard conditions. So now we're going to define different standard enthalpy changes. Okay, the first one we're going to look at is the standard enthalpy change of formation. Okay, the standard enthalpy change of formation. Right here we have delta H, right? For standard conditions we use the symbol theta. We have delta H theta, and then for formation we use the subscript F. Okay, so this symbol represents the standard enthalpy change of formation. The standard enthalpy change of formation can be defined as the enthalpy change. So this is the enthalpy change when, okay, this is the enthalpy change when when 1 mole of a substance, okay, when 1 mole of a substance in its standard state, okay, the standard state for a substance would be at room temperature and pressure, what state it's in, right? Liquid, solid, gas, right? In its standard state is formed from its constituent elements. It's formed from its constituent elements in their standard states under standard conditions. Okay, under standard conditions. So over here again you have to specify that it is referring to the enthalpy change when 1 mole, okay, when 1 mole of a substance is formed, okay, in its standard state from its constituent elements, in their standard states, okay, under standard conditions. Now standard conditions is obviously redundant, since if a substance is in a standard state and the elements are in the standard states, we have standard conditions. Okay, however sometimes they want this statement written. Okay, so just write under standard conditions as well. So let's look at the reaction for which the enthalpy change is the enthalpy change of formation of ethanol, right? So ethanol, the constituent elements that we have are carbon, right? We have carbon, we have hydrogen, and we have oxygen, right? So these are the constituent elements, right? And if you had to write this equation with state symbols, right, you're gonna write the state symbols for these elements in their standard states, right? The standard form of carbon is solid, okay, and when we talk about carbon in its standard state, okay, carbon in its standard state is graphite. Okay? Graphite is defined as the standard state for carbon, right? Then hydrogen is a gas, and oxygen is also a gas, right? And then the product that we have is ethanol, right? So this is the formula for ethanol. This is just C2H5OH, right? I've written this as CH3CH2OH, which is the correct way of writing the structural formula of ethanol, right? And then if we balance this equation, remember, it's defined as the enthalpy change when 1 mole of a substance is formed. So we're going to have 1 mole of ethanol, okay? And then we can say, okay, if we have 1 mole of ethanol, we have half a mole of oxygen, because we have 1 oxygen atom on the right. So over here we have 6 hydrogen atoms, right? 3 plus 2 plus 1, that's 6. We're going to have 3H2. Okay, we're going to have 3H2. And then we have 2 carbon atoms, right? So it will be 2C. All right, so this is the balanced equation for the enthalpy change of formation, or the enthalpy change for this reaction is the enthalpy change of formation of ethanol. It's the enthalpy change when 1 mole of ethanol in its standard state, that would be the liquid state, is produced from its constituent elements in their standard states under standard conditions. Okay, so the enthalpy change for this reaction is the enthalpy change of formation of ethanol. Now let's say I have the following reaction. Okay, I have the reaction H2, okay, H2 plus O2 gives me H2O. Okay, and I'm going to balance this equation like this. I have 2H2 and I have 2H2O. All right, and yeah, H2 is a gas, oxygen is a gas, and water is a liquid. Okay, so these are all in their standard states. What is the enthalpy change for this reaction in terms of formation enthalpies? The enthalpy change for this reaction in terms of formation enthalpies is 2 times the formation enthalpy of water. Okay, here we're making water in its standard state from its constituent elements in their standard states, but we're making 2 moles of water, right? If we're making 2 moles of water, right, the enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed. All right, if you're making 2 moles of water, this is basically you're making twice the amount of water. So that means you have 2 times the formation enthalpy. Okay, so the enthalpy change for this reaction is the enthalpy change when 2 moles of water are formed. So that would be 2 times the enthalpy of formation. All right, so this is the enthalpy change of formation, right? So for example, if I told you that the enthalpy change for this reaction, if I told you that the enthalpy change for this reaction was negative 572 kilojoules per mole, I want you to find the enthalpy change of formation of water. This would be the energy released if 2 moles of water were produced. So what would be the energy released if 1 mole of water was produced from its constituent elements? Okay, so that would be negative 572 divided by 2, which is negative 286 kilojoules per mole. So the enthalpy change of formation for different compounds is usually exothermic. Okay, it's usually exothermic. Not always, it can be endothermic as well, but most of the time is going to be exothermic. All right, it is the measure of stability of a compound, obviously relative to the constituent elements, right? So for example, the enthalpy change of formation of carbon dioxide is negative 394 kilojoules per mole. Okay, negative 394 kilojoules per mole, and the enthalpy change of formation of H2O is negative 286 kilojoules per mole. So which compound is more stable relative to its elements? So over here, if we add the constituent elements, if we add an energy profile diagram, right, or we're just looking at we were looking at energy on the y-axis, and we had elements here, right? Right, we can say that water is more stable than its constituent elements, right? It's at a lower energy, so the enthalpy change from elements to H2O is negative 286, right? That is for the formation of H2O from the constituent elements. On the other hand, for carbon dioxide, the enthalpy change is negative 394 from the constituent elements, right? So I can say that carbon dioxide is more stable or at a lower energy relative to the constituent elements. Okay, so this is how it's a measure of stability of a compound relative to the constituent elements. So over here again we can say that carbon dioxide is more stable relative to its constituent elements than water is compared to its constituent elements. Okay, because carbon dioxide is at a lower energy, right? Again, the enthalpy change of formation indicates how stable a compound is. Okay, and the more exothermic it is, the more stable that compound is relative to its constituent elements. Okay, more exothermic means more stable. Right. The last thing to note here is that the enthalpy change of formation of any element, okay, is equal to 0. Now that obviously lends itself from the definition, right? The definition says when 1 mole of a substance in its standard state is formed from its constituent elements in their standard states. So for example, we were talking about the enthalpy of formation of oxygen gas. We were talking about the enthalpy change of formation of oxygen gas, right? We would be forming 1 mole of oxygen. We would be forming 1 mole of oxygen gas from 1 mole of oxygen gas, right? So that would be this reaction. This is not a reaction at all, right? This is just the same thing. So the enthalpy change for this process is just 0. Okay, so by definition or from the definition, we can deduce that the enthalpy change of formation for any elements in their standard states will be 0. Okay, the enthalpy change of formation of oxygen, the enthalpy change of formation of nitrogen gas, okay, the enthalpy change of formation of nitrogen gas in its standard state, right? The enthalpy change of formation of, let's say, chlorine gas, etc. Okay, these will all be equal to 0. So it's important to note that each of these substances have to be in their standard states. Okay, it's not enthalpy change of formation of oxygen is 0. It's oxygen in its gaseous state under standard conditions. Okay, if you were making oxygen liquid or liquid nitrogen, for example, the formation enthalpy for those would not be 0 because those are not elements in their standard states. Okay, the enthalpy change of formation, the standard enthalpy of formation of elements is 0. That is when elements form in their standard states. Okay, that enthalpy change is defined to be 0. Now we were just talking about the enthalpy change of formation, not the standard enthalpy change, but just the enthalpy change of formation, right? Then the enthalpy change of formation, is defined as the following. Okay, the enthalpy change of formation, right? Now it's no longer standard enthalpy change. The enthalpy change of formation is just delta HF. Okay, and this is defined as the enthalpy change is the enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states. Okay. So here your elements have to be in standard states, but your products do not have to be in standard states. Okay, and the final conditions do not have to be standard conditions. Okay, so enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states. Okay. In their standard states. Okay, we're primarily going to be looking at standard enthalpy changes of formation, but this is when it's non-standard, right? So this could also refer to something like the formation of liquid nitrogen from gaseous nitrogen in its standard state, right? So if you were doing something like this, right, if for example you were going from nitrogen gas in its standard state to liquid nitrogen, right? This condensation, right? This would be the enthalpy of formation of liquid nitrogen. Now, liquid nitrogen obviously is not a standard substance. So therefore, the standard enthalpy change wouldn't apply here because this can't exist under standard conditions. Okay, so then this would just be you're forming liquid nitrogen in a non-standard state from the element in its standard state. Okay, and this enthalpy change here, for example, would be exothermic, right? Because it's condensation, right? Condensation is exothermic, whereas boiling or the reverse is endothermic. But again, whenever we're talking about enthalpy changes of formation, you will always have elements in your reactants, okay? And you'll always be making 1 mole of product. Okay, otherwise it wouldn't be an enthalpy change of formation. Okay, so this can be said to be the enthalpy change of formation of liquid nitrogen. Okay, because we're making liquid nitrogen from the element in its standard state. We're making 1 mole of liquid nitrogen from the element in its standard state. So now we're going to define what we mean by the standard enthalpy change of combustion. Okay. Standard enthalpy change of combustion. Now we've already defined enthalpy change of combustion, right? The standard enthalpy change of combustion is basically it's the same thing, but the reaction is being carried out under standard conditions. Okay, so what we have here is standard enthalpy change of combustion is the enthalpy change. Okay, is the enthalpy change when 1 mole of a substance, 1 mole of a substance is completely combusted, okay, or 1 mole of a substance in its standard state, okay, in its standard state is completely combusted to form products in their standard state, okay, to form the combustion products in their standard state, okay, to form products in their standard states under standard conditions. So the symbol that we use for this is just delta HC, right? But in this case, we also have a theta to denote standard conditions. Okay, delta HC is enthalpy change of combustion, but the theta means that it is the standard enthalpy change. Okay, so standard conditions. So for example, if we were talking about the standard enthalpy change of combustion of ethane, we would have ethane, in its standard state, which is gas, right? Ethane is a gas. It would react with oxygen to form carbon dioxide and water, right? Now here all the reactants and products have to be in their standard states. Okay, so oxygen is a gas, carbon dioxide is a gas, and H2O is a liquid. Now over here, if we're talking about the standard enthalpy change of combustion of ethane, okay, we have to make sure that we're combusting 1 mole of ethane. Okay, that would be the enthalpy change when 1 mole of a substance is combusted. Okay, so over here we're looking at the reactant being combusted. Okay, we're looking at a reactant being completely combusted. Okay, I would also mention in excess oxygen. Okay, I would also mention in excess oxygen. Right, completely combusted in excess oxygen to form products, okay, in their standard state under standard conditions. Right, so here you'd have 1 mole of ethane being combusted to form 2 moles of carbon dioxide, right, and then we'd have 3 H2O, right, because we have 6 hydrogen atoms, so that's 3 H2O, and then we just balance the oxygens. We have 4 plus 3, 7 on the right, so we would have 7 over 2 O2. So the enthalpy change for this reaction, as I've shown it, would be the standard enthalpy change of combustion of ethane. Okay, would be the standard enthalpy change of combustion of ethane. Let's say I have the following equation. Okay, I have the equation C4H10. Okay, that's butane gas reacting with oxygen gas, okay, to form carbon dioxide gas and H2O. Okay, and this reaction is taking place under standard conditions. So over here, let's say that we have 2 moles of butane being combusted. Okay, that means we have 8 CO2. We have 8 CO2 and we have 8 CO2 and we have 10 H2O, right? So on the right hand side, we have 8 times 2, which is 16, plus 10, that's 26 oxygens, right? So on the left hand side, we will have 13 O2s, okay? And the enthalpy change for this reaction, under standard conditions is negative 5,754 kilojoules per mole, right? So we can say that the enthalpy change of combustion of butane, okay, would be this value divided by 2, because this is the energy released, or this is the enthalpy change when 2 moles of butane are combusted. So the enthalpy change when 1 mole of butane in its standard state would be combusted would be this value divided by 2, which is negative 2877 kilojoules per mole. Okay. Now, of course, the standard enthalpy change of combustion, right, is an exothermic reaction. Okay. So again, combustion is always exothermic. Okay. Combustion will always be exothermic. So you'll always release, there will always be a release of heat if something is completely combusted in excess oxygen. Alright, so now we're going to look at some reactions for which the enthalpy change, can be an enthalpy change of combustion and an enthalpy change of formation. So for example, right, let's say we have the following reaction. Let's say we're talking about the combustion of hydrogen gas, okay, under standard conditions. Now, talk about the combustion of hydrogen gas, right? We're going to react hydrogen gas with excess oxygen gas to form H2O, right? And under standard condition, that's a liquid, right? And here, since we're talking about the standard enthalpy change of combustion of hydrogen, right? We're going to have 1 mole of hydrogen being combusted, right? Which means we have half a mole of oxygen gas and we have 1 mole of liquid water. Now, the enthalpy change for this reaction, right? The enthalpy change for this reaction is the standard enthalpy change of combustion of hydrogen. So this reaction again, right? The enthalpy change, as I've shown it, is the standard enthalpy change of combustion of hydrogen, because we're combusting 1 mole of hydrogen in a standard state in excess oxygen, right, to form product in a standard state, right? But the enthalpy change is also the enthalpy of formation, right? The standard enthalpy change of formation of H2O, right? So for this reaction, right, the enthalpy change is both, right? The enthalpy change is the standard enthalpy change of combustion, because 1 mole of hydrogen gas is being combusted in excess oxygen, right, to form water in its standard state. Okay. However, there's also the enthalpy change of formation of water, because 1 mole of water in its standard state is being formed from its constituent elements. So we can say that the enthalpy change of combustion of hydrogen is equal to the enthalpy of formation of water. Okay, or the standard enthalpy of combustion of hydrogen is the same as the standard enthalpy of formation of water. Okay, and the reason we can say that is because 1 mole of hydrogen, right, is 1 mole of hydrogen, right, undergoes complete combustion, right, complete combustion to form 1 mole of water. Right? So this statement alone explains why these two are the same, because you're forming 1 mole of a substance from its elements in their standard states, and it's a result of 1 mole of another substance undergoing complete combustion. Okay, so we can say this statement explains why the enthalpy of combustion of hydrogen is equal to the enthalpy of formation of water. Okay, enthalpy of combustion of hydrogen is equal to the enthalpy of formation of water. So yeah, the enthalpy change for this reaction can be referred to as the enthalpy of combustion of hydrogen or as the enthalpy change of formation of water. Okay. We have a similar thing. We have a very similar thing with carbon, right? we have carbon in its solid state. Remember, this is graphite. That's the standard form of carbon, right? When it reacts with oxygen, right, we can form carbon dioxide. And here, if we're talking about the standard enthalpy change of combustion of carbon, right, we're going to have 1 mole of carbon being combusted, right, in excess oxygen to form 1 mole of carbon dioxide. So, the enthalpy change for this reaction can be referred to as the standard enthalpy change of combustion of carbon, or as the standard enthalpy change of formation of carbon dioxide. So in this case, again, the reason we can say that that the enthalpy change for this reaction can be referred to as the enthalpy change of combustion of carbon or as the enthalpy change of formation of carbon dioxide is because 1 mole of carbon, okay, 1 mole of carbon undergoes complete combustion to form 1 mole of carbon dioxide. Okay, 1 mole of carbon undergoes complete combustion to form 1 mole of carbon dioxide. Okay, to form 1 mole of carbon dioxide.